Mathematics is the most beautiful and most powerful creation of the human spirit. Good morning to one and all. It's a delight pleasure in welcoming our principal, Dr. Santosh Babu, Secretary, Sri Ashok Kumar Untara, Head of the Department, Professor Venkat Raman, all the faculty members, and all the participants for this webinar on explorations in number theory, organized by the Postgraduate and Research Department of Mathematics, DG Vaishnav College. Prayer is the rising of one's mind and heart to God. We begin our today's session with Tamil Thai Varthu, followed by college prayer.
நீராறும் கடலொடுத்த நிலமடந்து எழிலொழுகும் சீராரும் வதனமென திகழ்வரத கண்டமிழி எக்கணமும் அதிசிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
सत्यव्रतं सत्यपरं त्रिसत्यं सत्यस्य योनिं निहितं च सत्ये सत्यस्य सत्यं ऋतसत्यनेत्रं सत्यात्मकं त्वां शरणं प्रपन्नाः वाणी गुणानुकथने श्रवणो कथायां हस्तौ च कर्मसु मनस्तव पादयोर्नः स्मृत्यां शिरस्तव निवास जगत्प्रणामे दृष्टिस्ततां दर्शनेस्तु भवत्तनूनाम् नमो भगवते तस्मै कृष्णायाद्भुतकर्मणे रूपनाम विभेदेन जगत्क्रीडति यो यतः ओम शांति शांति शांति.
I request Dr. Jain Karthik, Associate Professor, Postgraduate and Research Department of Mathematics, DG Vaishnav College, to prelude about the seminar.
Good morning. On behalf of the graduate postgraduate research department of mathematics, DG Vaishnav College, I am happy to welcome you all to the national webinar on explorations in number theory. Number theory has always fascinated amateurs as well as mathematicians. In contrast to other branches of mathematics, many problems and theorems of number theory can be easily understood by all, whereas the solutions of the problems and proofs of the theorems require sophisticated mathematical packages. German mathematician Gauss once said, "Mathematics is the queen of sciences, and number theory is the queen of mathematics." Initially, number theory was considered purest branch of mathematics, with no direct application to the real world. The improvements in computer technology enabled number theories to give remarkable advances in factoring large numbers, determining primes, testing conjectures, and solving numerical problems once considered out of reach. Encryption is the method by which information is protected by converting it into secret code. The difficulty of guessing this information is what makes encryption such a valuable security tool. Encryption has been used for protection of information. It was initially used by militaries and governments. In modern times, encryption is used to protect data stored on computers and storage devices, as well as data in transit over networks. Today, encryption is an integral part of many tools, protocols we rely on, like credit cards, online bank transactions, etc. Today's webinar will be on explorations in number theory, presented by Dr. R. Sivaraman, Associate Professor, Department of Mathematics. Over to you, ma'am. Thank you.
Thank you, sir. Dear participants, you can post your queries and comments in the chat box. Feedback link will be given towards the end of this session. Now, I welcome Dr. Hariharan, Assistant Professor, Postgraduate and Research Department of Mathematics, DG Vaishnav College, to introduce the speaker of the day, Dr. Sivaraman, Associate Professor, PG and Research Department of Mathematics, DG Vaishnav College.
Good morning to one and all. I am very happy to introduce the resource person for this one-day national webinar on exploration in number theory. Dr. R. Shivaraman, working as Associate Professor at DG Vaishnav College, Chennai, has 22 years of teaching experience. He has been conferred with the National Award for Popularizing Mathematics among Masses in 2016 by Department of Science and Technology, Government of India. He was also conferred with the prestigious Indian National Science Academy Teaching Award for the year 2018. He has also received 2 state government Best Science Book Awards in 2011 and 2012. For his contribution to mathematics, he has won more than 50 prestigious awards so far. He has provided more than 300 lectures conveying the beauty, importance, and applications of mathematics. He has published more than 70 research papers in mathematics. He was member of editorial board for more than 10 journals in mathematics. He was a member of the textbook writing committee, Tamil Nadu School Education Department, for preparing revised mathematics textbook for 11th class and chairperson for 10th class. He writes articles and provides puzzles for famous newspapers like the New Indian Express, Times of India, the Hindu School Edition paper, Tamil Nadu, Dinamalar Pattam newspaper. He has also contributed several articles about mathematics in monthly magazines like Ariviyal Oli, Chennai Report, Arumbu, and continue to contribute more. He is currently editor of the journal Junior Mathematician, a quarterly magazine for school students published by AMT. He is also editor of the e-magazine Mathematics Pixels, published by Pi Mathematics Association. For the past 22 years, he teaches most deserving and poor students and made their life to have better living. In view of spreading mathematics among everyone, with the help of his students and well-wishers, he had initiated an exclusive charitable trust, Pi Mathematics Association, being its founder trustee since June 2007. Serving the poor and needy students was his life motto. With that introduction, I request Shivaraman sir to give his wonderful lecture on explorations in number theory. Thank you.
So, good morning to one and all. So, I feel very happy to be amongst you in presenting this topic, in the topic where I like most. Numbers are very special to everyone, in particular to people like me, because numbers convey so much meaning. So, I will begin my presentation in the topic explorations in number theory. So much of research has been done in number theory for the past many years. Is the screen visible, sir? Hello? Is the screen visible?
Yes, sir.
Okay. Thank you. So I will begin my top lecture in the topic explorations in number theory. This is, I mean, the one that I love most among all mathematicians was Ramanujan. He is my idol for every action that I do. So I always pray him before I begin with anything. And this is the magic square constructed for the date of Ramanujan, not constructed by Ramanujan as many sources claim. This is constructed by myself, which contains today's date, as you can see marked in the green color, 6/2/2021. So you can add special numbers according to your choice and construct such magic squares. And it also contains tomorrow's date, 7/2/2021. The reason for including tomorrow's date is clear when I show the next slide to you. So this is the kind of puzzle or riddle that I have constructed in the spirit of works of Ramanujan. Ramanujan was master in creating such wonderful puzzles, and getting a clue from his work, I had created this puzzle. Okay, so we will discuss about the answer later on. So I dedicate this presentation to two important mathematicians. One is Pythagoras, who's rightly credited with the title father of numbers. So Pythagoras is called father of numbers, and one of my very favorite mathematicians. And of course, tomorrow actually is birthday of G.H. Hardy, one of the very famous mathematician in England who helped Ramanujan. Without Hardy, we could not have known Ramanujan as of today. So I dedicate this presentation to these two great men. So I begin my topic. See, my presentation would mostly be understood by students. So I have not gone to research level or very, very deep level. So I had taken care that it can be followed by everyone. Most possibly, I will manage with that level. If some cases, if you have any doubts, you can post it at the end of the lecture. So if you will begin with number, say number here refers to in number theory, usually in analytic number theory, when we say a word number, it refers to natural number. So there's not any other number like rational number or irrational number or something. Okay. So whenever I say number, it refers to natural number. So if I take a number like 10, you take the divisors of 10, leaving 10. See, you take the proper divisors of 10 and add them. So supposing if I have a number 10 with me, the proper divisors of 10 are 1, 2, and 5. Any number divides itself, so exclude that divisor and then take the remaining smaller divisors. If you exclude a number from the collection of divisors and add them, such collection of proper divisors is called aliquot divisors, and this sum is called aliquot sum of divisors. So what I do is, any number divides itself, I am going to take proper divisors of 10, which are 1, 2, and 5, and add them. You get 8. The answer is less than the given number. As you see, 8 is less than 10. If in case you take a number and add its proper divisors, if in case you get an answer less than the given quantity, it is called deficient number. So 10 is a deficient number. Deficient sense, it is something less than the expected answer. I want to get something which is equal to 10, but unfortunately I'm getting a number which is 2 less than 10. So it's something less than the required value. So it's called deficient. Deficient means less than what I expect. Okay. So if you take a prime number like 11, see, any prime number p will have only two divisors, namely 1 and p, and therefore the proper divisor of any prime number, not just 11, is simply 1, and 1 is clearly less than 11. Therefore any prime number for this matter will be deficient number. So if you take a prime number p, it has only two divisors, namely 1 and p, and I have to exclude the given number. So if I exclude p, I get only 1. So any prime number will be, and that 1 will be less than the given prime number p. Therefore any prime number is automatically a deficient number. There's no problem. Whereas if you take a number like 12 and add the proper divisors of 12, you get 1 plus 2 plus 3 plus 4 plus 6. That adds up to 16. And this sum is greater than the given number. So such number, if you get an answer more than the required value, the taken number, then it's called abundant number. Abundant means more, deficient means less. Deficient is less than you get an answer less than the required number. Here you get an answer more than the required number. So it's called abundant. Abundant means more than what you expect. Okay, abundant. Abundant refers to more than what I get. Okay, what should I get? So 16 is greater than 12. Therefore, 12 is an abundant number. In fact, 12 is the smallest abundant number. Okay, there are several other numbers also. Whereas if you take numbers like 6 and add the proper divisors, you exactly get 6. So such numbers are called perfect numbers. So perfect in the sense, if you take a number, add its proper divisors, sometimes you get less than the given number, that sum will be less than the given number. Such numbers are deficient. Sometimes you get more than the given number. Such numbers are abundant. So neither less nor more. If you get exactly the same number, in that sense, it is exactly because I am getting perfectly the given numbers. It's called perfect numbers. Perfection is for numbers, like perfect numbers, is viewed in two ways. One possible way is through this way. I mean, neither less nor more. You get exactly the same answer. In that sense, if the sum of divisors of a proper divisors of a given number is itself, then such a number is called a perfect number. And perfect numbers were not new discovery. These were known to earlier Greeks. In fact, they knew the first 4 perfect numbers. 28 is the second perfect number, because if you add proper divisors of 28, namely 1, 2, 4, 7, and 14, you get the same answer, 28. For 496, if you add such thing, you get exactly 496. If you take 8128, if you add the proper divisors of 8128, you get the same answer, 8128. So these were not new to us. These 4 numbers were known to in the Greek period itself. And mathematically, see, because we are excluding the number itself. So supposing if you take 6, if I include 6, then I get a 12, and that answer will be twice the given number. See, perfect numbers are defined in 2 ways. One way is to view in the fact that if the sum of the proper divisors is the number itself, then it is called perfect. Or if you add all the divisors of the number including itself, then you should get twice the given number. And that happens here, because if you add 6 here, if you include the 6 also and then add to the remaining divisors, you get 12. 12 is twice 6. In fact, 28 here, this numbers will add up to 28 already. So if you add the divisor 28 here, you get 56, and that is twice 28. Similarly, n is perfect. If sum of sigma n, this sigma n denotes sum of all divisors of n, natural number n. So sigma n is notation for denoting sum of all divisors of natural number n. If sum of all natural numbers of a number is twice a number, then the number capital N is called a perfect number. Okay. This is equivalent to saying sum of aliquid divisors is a number itself. Both are equivalent definitions. Okay. This is sum of aliquid divisors. This is sum of all divisors. Okay. Now, if you can get some pattern for this perfect number. How do we know these numbers exist? Okay. So these are how do we identify? Is there any pattern behind the perfect numbers? To identify the pattern, we make this factorization. One thing that we can observe is all the numbers that I have listed down here turns out to be even number. Okay, and any even number has 2 as a factor. Okay, so if you can factorize, you can write 6 as 2 times 3. This 2 I can write to get some pattern. I'm rewriting this way. This 2 is 2 to the power 1. This 3 is 2 square minus 1. 28 is 4 times 7. 4 is 2 square, and 7 is 2 power 3 minus 1. 496 is 16 times 31. So each case you see any perfect number is 2 to the power something into the 2 to the power next number. That is, if it is 2 square, it is next power of 2, which is 2 cube. If it is 2 power 4, the next power of 2, 2 power 5 minus 1. If it is 2 power 6, the next power of 2, 2 power 7 minus 1. In general, if you take any perfect number and factorize as 2 power something, the second factor will be 2 to the power 1 more than this number subtracted with 1. So that is how the pattern for perfect numbers look like. But to be more precise, we will prove this theorem. It was Euclid who gave this proof in the around 3rd century BCE in his monumentary excellent work called Elements. Elements, incidentally, was the first recorded work on mathematics, just like Tolkappiyam to Tamil. It was considered to be the Bible for mathematics. Okay. So if 2 power n minus 1 is prime, according to Euclid's theorem, Euclid proved this actually. So what he said was the perfect number has this wonderful characterization. generalizing this format, you can prove a more general result. Euclid said that if 2 power n minus 1 is prime, then capital N, which is 2 power n minus 1 times the next power of 2 here. So if this number is prime, then taking that as one of the factor and multiplying it by 1 power less than this, because that is how we saw here. If it is 2 cube, this is 2 square, 1 power less than that. If it is 2 power 5, this is 2 power 4. If it is 2 power 7, this is 2 power 6. So in general, if you take this as a factor and assume this as a prime number, you can also see that these numbers are prime numbers, 3, 7, the second factors. The first factors are powers of 2 and second factors are powers of, they are prime numbers. And prime, any number of the form 2 power n minus 1, which we have taken here, are called Mersenne numbers, named after French mathematician and monk Marin Mersenne. He was considered to be an amateur mathematician, but he corresponded and collaborated with all other mathematicians like Fermat and other famous mathematicians during this time, Descartes and other people, and he spread the mathematics through them. He passes the information from one mathematician to other mathematician. He involved, just like a postmaster, he was doing all kind of help to the development of mathematics. So to honor him, numbers of the form 2 power n minus 1 were called Mersenne numbers. In particular, if this number happens to be a prime number, then it is called Mersenne prime. Okay, Mersenne, Mersenne, Marin Mersenne was a Frenchman, and so Euclid showed that if 2 power n minus 1 is prime, then this product is also a perfect number. So to prove something is a perfect number, according to the definition, you can show that sum of all the divisors of n is twice in number, 2 times n. This is the way you can, using this definition, basic definition. Either you can show the sum of all the divisors of a given number is twice in number, then it's perfect, or sum of the proper divisors of n is itself, then it is perfect. Both are equivalent. Okay. So before going to this proof, I give some basic things. So if you add all divisors of 2 power k, numbers of the form 2 power some number, say k, see 1 divides 2 power k, 2 divides 2 power k, 2 square divides 2 power k, 2 power k minus 1. The divisors of 2 power k are 1, 2, 2 square, 2 power k minus 1 and 2 power k. 2 power k is the maximum possible divisor dividing 2 power k. Any number divides itself, and that is the largest possible divisor. So if you add all the divisors of 2 power k, by geometric series formula, this is of the form 1 plus r square up to r power k, which is r power k plus 1 minus 1 by r minus 1. Here the common ratio r is 2 for you, and since the denominator is 1, I get just enumerated. This is 2 to the power k plus 1 minus 1. So which means that if the sum of all divisors of the numbers of the form 2 power k is next power of 2 minus 1. So if you want to find, say for example, sum of divisors of 2 power 5, for example, the answer will be 2 power 6 minus 1. Sum of all divisors of 2 power 10 is 2 to the power 11 minus 1. The next power of 2 subtracted with 1. So this is how this formula says. We are going to make use of this here. And sum of all divisors of prime number p, because prime number p has just 2 divisors, 1 and p, clearly this required sum is p plus 1, because 1 is a divisor of any prime, and p is, and prime number only has exactly 2 divisors, namely 1 and p, and therefore if you find sigma p, it is just p plus 1, because these two are the only possible divisors of any prime p. So if you now calculate sigma n for this particular value, what will happen? For this choice of n, I want to prove that sigma n is 2n, then n will become perfect. So sigma n is sigma of, and so sigma of m times n, divisor function is multiplicative in the sense that sigma mn is sigma m into sigma n, just like what you did in your algebra course for homomorphism. Phi is said to be homomorphism if phi of ab is phi of a times phi of b. Similarly, divisor function sigma is a multiplicative function, meaning that sigma mn is sigma m into sigma n, provided mn are co-prime. That is, GCD of these two numbers are 1, and the GCD of these two numbers are clearly 1, because you know the 2 power n minus 1 divides 2 power n, the next number, and 2 power n minus 1, 2 power n minus 1, and the and 2 power n are co-prime. Therefore, these two numbers are co-prime. That means GCD of these two numbers. As you can see here also, GCD of 2, 3 are 1, GCD of 4, 7 is 1. See, because this number is 1, then twice this number. And therefore, twice this number is an even number. Okay, so 1 is twice this number is next power of 2, and two consecutive numbers are always co-prime. Therefore, 1 less than that compared with the previous power of 2 is always co-prime, and therefore these two numbers are co-prime. See, for the sake of completing the task of finishing the lecture, I will probably go through some of the ideas very quickly. You can note it down and verify later. You can note down, especially interested students can note it down and verify the claims that I'm making later. So these two numbers are co-prime, and therefore, because sigma is multiplicative, sigma of n is sigma of the first number times sigma of, because these two numbers are relatively prime, sigma of mn is sigma m into sigma n. So I multiply these two numbers and I use this property. Sigma of 2 power k is next power of 2 minus 1. That is sigma of 2 power k is 2 power 1 more than this number, k plus 1 minus 1. So sigma of 2 power n minus 1 is 2 power n, the next power of 2, which is n minus 1 added to 1 is 2 power n, next power of 2 minus 1. And 2 power n minus 1, this number is assumed to be prime. And we know that sum of divisors of any prime number p is p plus 1, one more than that. So if I assume that 2 to the power n minus 1 is prime, then sigma of 2 power n minus 1 will be, because this is a prime number according to our assumption, this will be 1. The answer is 1 more than this. So if you add 1 to this 1 will cancel, you get 2 power n. And this I can write as 2 times. You can write 2 power n as 2 times 2 power n minus 1. So write this as 2 times 2 power n minus 1. Keep this factor as it is. Now this is precisely n according to our assumption. This number, this quantity is n. So if I compute sigma n, I get 2n. Therefore, n is perfect. And this proof was given by Euclid some 2,300 years ago. So Euclid gave a characterization of prime number of perfect numbers, assuming that this is prime. But then a natural question would arise for us. Then is it not easy to generate all perfect numbers if you know a particular form like this? But this particular form being perfect is obtained only by this assumption. But the problem now is that we do not know for what choice of n 2 power n minus 1 is prime, except the fact that we know certainly that 2 power n minus 1 is prime only if n is prime. So only if n is prime, this quantity will become prime. If n is a composite number, then this will not be a prime number, it will be a composite number. So that part we know, but we are not sure for what choice of n, which is a prime number, this quantity becomes prime. For example, 2 power 11 minus 1 is not a, if you take 2 power 11 minus 1, that is not a prime number, though 11 is a prime number. So it is difficult to manage with it. Okay, that's the challenge for the mathematicians, and that prevents us to generate all perfect numbers as easily as possible, though we know a particular form for it. Thanks to Euclid for proving this. And now Euler did the converse part. Nearly after 1800 years or nearly after 2000 years or so, during Euler's time, he proved the other way. That is, he proved that all even numbers of this form were perfect number and he proved that he proved that if n is an even perfect number, this is an even number clearly, because you multiply by 2 power something, and 2 power n minus 1 is an even number. So even number times whatever you multiply, whether it be odd or even number times any number is even. So Euler showed that all even perfect numbers would be of this form. So if you assume that n is an even perfect number, then n can be written in this form. The other converse part of, or other way of this, what Euclid did was he assumed that this is prime and proved that this is perfect. What Euler did was he knew that this is an even number. That's clear, because I told you before that all listed perfect numbers were even numbers. What Euler did was he proved was that, well, you can't find a perfect number of the form, say 400, which is also an even number, or 300 or 100 or something. No even number will escape from this pattern. So if you get a perfect number, it will only be of this kind. This is what Euler did. So for proving this, you assume n to be 2 power. I mean, I take this particular result for proving this. This is a little bit involved. Anyway, I'll rush through the process. If you know that 4 divides 12, then sigma 4 by 4, which is 7 by 4, will be less than or equal to sigma 12 by 12. So if you take generally two numbers m and n such that m divides n, then sigma m by m will be less than or equal to sigma n by n. This is a property which is you can prove easily. I'm not going to do it here, but I'm going to use this property here for proving this by. Of course, the proof given by here were not done by Euler. Euler's proof was a little lengthy, so it's done by some other mathematician. So let n be, capital N be 2 power n minus 1 times m. So this number I'm taking as m. So if I assume that capital N is 2 power n minus 1, 2 to the power n minus 1 times small m, then I should prove that, comparing these two, I should prove that m is actually 2 power n minus 1, and moreover I should prove that m is prime. So because according to Euclid's convention, this product here, if you multiply 2 power n minus 1 by 2 to the power n subtracted with 1, this factor should be prime number. So that is also I need to prove. So if I assume that capital N is 2 power n minus 1 times small m, then I should prove that m takes this form, namely 2 power n subtracted with 1, and moreover I should prove that this number is prime. We will do that. Okay. So if I take summation sigma n, I know that n is perfect here. Okay, I'm assuming n is perfect, and I want to show that m is this number. So sigma n, if I compute, and again, as I told you, this number is an odd number. M is an odd number. Okay, so as you can see here in this example, if for any perfect number, the first factors are powers of 2, second factors are odd numbers. So if this is 2 power something into m, this m should be an odd number. They are machine primes actually, because they are powers of 2 subtracted with 1. So this number m is an odd number, where m is odd. Since 2 does not divide m, it is relatively prime to 2 power n minus 1. M is, because this is an odd number and 2 does not divide m. 2 does not divide any odd number. Therefore, m is relatively prime to this. So these two terms are relatively prime, and therefore I can apply multiplicative property of the divisor function. So sigma n is sigma of 2 power n minus 1 times m, which is sigma of 2 power n minus 1 into sigma m. As we did before, summation of 2 power k is next power of 2 minus 1. So summation of 2 power n minus 1 is next power of 2, which is 2 power n minus 1 times sigma m. So I get a nice equation here. But because I assume that n is perfect, sigma n is 2n, therefore I can substitute 2n here in the left hand side. So that gives me 2n is equal to n, of course, is according to assumption is 2 power n minus 1 into m. So I substitute that here. 2 into 2 power n minus 1 into m is equal to, if you compute this product here, you get 2 power n times m. So left hand side sigma capital N will turn out to be 2 power n times m. So if I can substitute this answer here in this equation, you get 2 power n times m is equal to 2 power n minus 1 into sigma m. I have rewritten the same equation here. And you can also see that this number 2 power n minus 1 divides m, because this does not divide this. See, these two numbers are consecutive numbers. So this does not divide it. This is an even number, this is an odd number. So if this product is equal to this product, this should divide this. Okay, uniqueness of factorization. Now what I'm going to do is consider this ratio 2 power n by 2 power n minus 1. This is sigma m by m. So because 2 power, say this terms that we get here are because of the fact that this property, if m divides n, then sigma m by m is less than or equal to sigma n by m. Using this fact here, I know that 2 power n minus 1 divides m. Therefore, sigma m by m will be greater than or equal to sigma of this number, 2 power n minus 1 by 2 power n minus 1. So using that particular inequality, I got this answer. Okay, And this equation is obtained by rearranging the terms here. So I know this equation from the previous step here. So what I can do is group m one side and n one side. So you get 2 power n by 2 power n minus 1 is equal to sigma m by m. Regroup this equation, terms of this equation. And sigma, because m is 2 power n minus 1 divides m, sigma m by m will be greater than or equal to sigma of 2 power n minus 1 by 2 power n minus 1. And I do not know whether this number is prime, but any number will have automatically always two divisors, namely 1 and itself. So sum of divisors, if it is prime number, it is exactly equal to 1 plus that number, because sigma of p is 1 plus p. If it is a composite number, the sum will be more than 1 and itself. That is, if you take, for example, say number like composite number like 4, 1 divides 4, 2 divides 4, and 4 divides 4. Anyway, for any number, 1 and the same number divides itself. So sigma n, if it is a prime number, if n is a prime number, will constitute only 2 terms. If it is a composite number, it will contain more number of terms if you add. So this, I do not know whether this is prime. So, but what I know is sum of all divisors is greater than, keep the denominator as it is. If this is prime, this is exactly equal to this, but 1 always divides this number, and 2 power n minus 1 always divides this number. Because I do not know whether this is prime or not, but what I know is sum of any number, divisors of any number, is greater than or equal to these two divisors. There may be some more divisors also. I'm not sure about it, but anyway, it is enough to consider these two. So 1 and minus 1 will cancel, you get 2 power. So you see, these two terms are equal. So this is 2 power n by 2 power n minus 1 is less than or equal to this number. So if you get equality here only if m is equal to n. Okay, m divides n. In general, if m divides n, implies sigma m by m is less than or equal to sigma n by n. You get equal here only if m is equal to n. Because I get these two numbers equal, it should happen that sigma m by m should be equal to 2 power n by 2 power n minus 1. Therefore, m has to be 2 power n minus 1. And sigma m has to be 2 power n, the numerator. And I can write this as 1 plus 2 power n minus 1. M is 2 power n minus 1 for me. So sigma of m is m plus 1. I know the sigma of any prime number p is p plus 1. Because sigma of m is m plus 1 or 1 plus m, which is 2 power n minus 1 is prime. So this proves this part also. So what we have done is, we have shown that the second factor for capital N here takes this form, 2 power n minus 1. And not only that, we proved that that is also prime. So in a way, Euler proved that all even perfect numbers will look like this. But I can tell you, even today, no one had known whether odd perfect numbers exist. We are unsure about it, but most mathematicians believe that there is no odd perfect number, because extensive and exhaustive searches had been made by using several algorithms. And people had now found that up to 10 power 1050 or something, more than 10,000, up to 10 power 1000, there is no odd perfect number. And if at all such odd perfect number exists, it will have more than 37 prime factors. So it will be, even if it exists, it will be a very, very monstrously huge number. It's not going to be a small number like 6 or 28 or something like that. I don't know. I mean, people doesn't know, and they are not sure about whether such number even exists. Okay, so that's still an unsolved problem. Existence of odd perfect numbers, which is a very old problem, not solved till today. Okay, so if you take perfect numbers like 6, this is 2 times 3, I can write this 2 as this is write this 2 as 4 by 2. Keep this 3 as it is. You can write this because an even number, so write that as 4 by 2. And this number you can see is 1 plus 2 plus 3, because you know that 1 plus 2 plus up to n is n into n plus 1 by 2. So 3 into 4 by 2, I can write as 1 plus 2 plus 3, because if I add 1 to n, you get n into n plus 1 by 2. So because 3 into 4 by 2 is of the form n into n plus 1 by 2, I can write it as 1 plus 2 plus 3. Similarly, 28, I can write as 4 times 7. Keep the 7 as it is. Write 4 as 8 by 2. This is of the form n into n plus 1 by 2. So you see 1 plus 2 plus up to 7. You see a nice pattern here. For 28, the second factor is 7. So 28 is sum of first 7 numbers. The first perfect number 6 is 2 times 3. Therefore, 6 is sum of first three numbers. Okay. Similarly, 496 is 16 times 31, the third perfect number. So that is sum of first 31 numbers. You can see here. In general, the nth perfect number, this is an even number, this is an odd number. So keep this odd number as it is. Write 2 power n minus 1 is 2 to the power n divided by 2. Now this is how the form n into n plus 1 by 2, which is sum of first 2 power n minus 1 numbers. And sum of first k numbers, k natural numbers like this, are usually called triangular numbers, which I will come later on after some time. So what I'm going to do is I had gotten the form of perfect numbers. In fact, all even perfect numbers will look like this, and of this form. All even perfect numbers can be written in this form. And you know by Euclid that this is how perfect numbers will be, provided if this number is prime. So these are all some of the properties about perfect numbers. 28, for example, I can write it as sum of cubes, 1 cube and 3 cube. 496, so all even perfect numbers except 6. Excluding 6, all other perfect numbers, known perfect numbers, are sum of cubes of numbers. In fact, they are consecutive cubes. Okay. In general, there is a general theorem saying that if n is this number is perfect, then I can write this perfect number n as 1 cube plus 2, 3 cube plus 5 cube, all consecutive odd numbers. Okay, 1, 3, 5, 7, up to this number, 2 to the power n plus 1 by 2 minus 1 the whole cube. So I have given a small proof here. I will rush through the proof. I am going to take m as 2 power n minus 1 by 2. So the 2 times m, if you multiply this by 2 and apply a power m into a power n is a power m plus n, power rule formula, this will become 2m, 2 power n plus 1 by 2. And if you square m, this 2 will cancel, you get 2 power n minus 1. This 2 power n minus 1 is here. So this is m square, okay, according to our conversion. I'm converting this problem from small n to small m, just for convenience. So what I do is I add this 1 cube plus 3 cube plus 5 cube up to this number. Remember, 2 power n plus 1 by 2, according to our assumption, is 2m. So this is 2m minus 1 whole cube. And this is sum of all odd cubes. Sum of all odd cubes is sum of all numbers from 1 to 2m. Minus I subtract even, because there's only odd numbers that I have here. Sum of cubes of odd numbers. Here I include sum of cubes or odd numbers as well as even numbers here. So I have to subtract that with sum of cubes of even numbers. And sum of cubes of first k numbers, like 1 cube plus 2 cube up to k cube. You know that is k square into k plus 1 whole square by 4. You could have done it in lower classes. Because of the sum of cubes formula, I write this 1 cube plus 2 cube up to k cube is k square into k plus 1 whole square by 4. Similarly, you can take 2 cube common, then you get 1 cube plus 2 cube up to m cube and apply this formula here. 2 cube is 8, 8 divided by 4 is 2. So you can club the other terms. This 2 square is 4, so this 4 will cancel with this 4. You get m square and 2m plus 1 whole square. Simplify. What you get ultimately is this term. And here you see m square is 2 power n minus 1. The first term here, this is m square is 2 power n minus 1, the first term. And 2m square minus 1. What is 2m square? See, m square is 2 power n minus 1. 2m square is 2 power n. So this is 2 power n minus 1. So if you just substitute m in terms of n, you get this answer. Therefore, if I add this collection of cubes, you get precisely capital N. So any perfect number apart from 6 can be written as sum of this many cubes, consecutive cubes. So many, of course, knew this property from textbooks, but they have not probably have seen the proof. So I want to give idea of proving things here. Okay, so this is a very old but very beautiful problem, the idea of perfect numbers. So I thought of including this to you rather than going for harder things. Okay, so if n is 2 power n minus 1 into 2 power n minus 1 is perfect, and if n is written in base 2 numbers, then the theorem says it will have 2n minus 1 digits, the first n or unity and the last n. See, if you take 6 for example, 6 can be written as 110 in base 2 binary expansion, in which 2 digits are 1, the other last digit is 0. So the number of digits with 1 will be 1 more than number of digits with 0. That is what it says. And moreover, 6 is, listen, 2 power 1 into 2 square minus 1. So if it is written as this many numbers, if it the second factor is 2 power n, then the number in binary expansion will become 2n minus 1. The easy way to identify this number is the number of digits in the binary expansion is 6 is close to 8, 8 is 2 cube, which is so the power of 2 is 3, therefore it contains 3 digits here, out of which two digits, the first 2 digits will be 1 and the last digit is 0. Similarly, 28 is near to 32, the next power of 2, which is 2 power 5. Because power of 2 is 5, there are 5 digits here, in which first 3 digits are 1, the last 3 digits are 0. Okay, so that is how it goes. 496 is close to 512, which is 2 power 9. So this contains 9 digits, in which first 5 digits are 1, the last 4 digits are 0. So the theorem says you always get a number in the binary expansion in which the number of ones will be 1 more than the number of zeros. That is one of the other characterization of perfect numbers. And any even perfect number will always end with either 6 or 8. I use this property here. 6 power m is congruent to 6 mod 10. That is, if you take power of 6 anytime, so 6 power will always end with 6. Therefore, if you divide by 10, the remainder will always be 6. Okay, so this is not very difficult to see. And if you apply this idea here, any prime number greater than 2 will be of the form 4n plus 1 or 4m plus 3, except 2. Okay. And if you assume the prime numbers are the form 4n plus 1 and substitute here in this perfect number formula, upon taking reminders, you see the remainder is 6. So if you raise 2 to the power prime number of this form, you always get an answer ending with 6. Similarly, if you raise power of 2 to the prime number of this form 4n plus 3, then you see the answer is 4 times 7, that is 28. So it will end not only with 8 but in 28. In fact, 6 and 28 are the first 2 perfect numbers. So if you see the list of perfect numbers, it either ends with 6 or with 28. So last 2 digits will either be 28 or the first digit will be 6. Either it ends with 6 or it ends with 28. The reason is because proved here. So this is 4 times 7, 28. It will either end with 28 or simply 8, whatever it is. And then this great mathematician Van Zyl proved that sum of digits of even perfect number apart from 6 is always 1. That means if you take leave 6, exclude 6 from this, just like sum of cubes, we excluded 6. Apart from the number 6, if you take any other perfect number, add the digits. If the answer is 2 digits or more, you again add them and make it a single digit. That answer is actually called the digital root of the number. Okay, so find the digital root of all these numbers. You always get 1 if it is a perfect number. So 2 plus 8 is 10. Because answer is a 2-digit number, you add again 1 plus 0. 1 plus 0 is 1. So you always get 1. 4 plus 9 is 13. 13 plus 6 is 19. You get 1 plus 9, 10. 1 plus 0 is 1. 8 plus 1 is 9. 9 plus 2 is 11. 11 plus 8 is 19. 1 plus 9 is 10. So you get 1 plus 0 is 1. So in fact, this will be true for any perfect number that we know as of now. So the next thing that I want to tell you is, if you take any perfect number, take these devices and reciprocals of the devices and add them. You take any perfect number, take the reciprocals of the devices. 1, 2, 3, 6 are devices of 6. If I take reciprocals of those devices, I get 1 by 1, half, 1/3, and 1/6. If you add them, you always get 2. This is true for any perfect number. If n is perfect, then this sum of reciprocals of its devices will be of the form sigma n by n. But by definition, if n is perfect, sigma n is 2n. So you get 2n by n. That is true. In fact, if you do the same process for deficient numbers, sigma n will be less than 2n. And therefore, you get an answer less than 2 for deficient numbers. For abundant numbers, this sum of reciprocals of the divisors will be greater than 2. So this 2 acts as a threshold number or limit number, which helps you to decide if a number is deficient or abundant or perfect. Okay, so that kind of beautiful property that you get here. And I told you that it is rather difficult to, just few minutes back I told you 2 power 2 minus 1 is prime, 2 power 3 minus 1 is prime, 2 power 5 minus 1 is prime, 2 power 7 minus 1 is prime, but 2 power 11 minus 1 is not prime. Okay, so the problem lies in the difficulty of choosing the prime p for which 2 power p minus 1 is prime. It will not be true that for all primes p this number is always prime. So that is a problem. So you can see here in this list, for 13, 17, 19 you get prime, but for 23, which is the next prime, and 29, 2 power 23 minus 1 and 2 power 29 minus 1 are not prime. They are composite numbers, whereas 2 power 31 minus 1 is prime number. And this are the first list of first 8 perfect numbers. You see, the perfect numbers grow very large in size as you keep on moving. And because we proved that all perfect numbers either end with 6 or 8, as you can see. In fact, not only 8, it will end with 28. 28 will be the last 2 digits. Either it ends with 6 or it ends with 28. And incidentally, 6 and 28 are the first two perfect numbers. And this is the largest perfect number that we know as of today. This is the largest Mersenne prime. The largest prime that we discovered today are usually of the form Mersenne primes, generally. And this is the latest discovered prime number, Mersenne prime. So this is 2 power p minus 1, and this is 1. This power is 1 less than this, because by Euclid's theorem, 2 power n minus 1 into 2 power n minus 1. So this power of 2 is 1 less than this power. So keeping this in mind, this takes this form. So this is a prime number, namely 82589933. This number is a prime number. So if you raise 2 to this prime number and subtract 1, that will contain 24,862,048 digits. This prime, this Mersenne prime. So this product will contain approximately 50 million digits. So this is the largest perfect number that we know as of today. In fact, this is known to be the 51st perfect number. So among all class of numbers, infinitely many numbers that exist, we only know, till today, we only know 51 perfect numbers. This is the latest discovery made in December 2018, not very back, long back. Just a couple of years back in December 2018, this was discovered, and search for finding new Mersenne primes as well as new perfect. See, once you discover a Mersenne prime, automatically that gives a perfect number, because what you have to do is multiply a Mersenne prime with the power of the index of the Mersenne prime, take the 1 less than this and multiply with this number, you get. So each time when a new Mersenne prime is discovered, that will automatically give rise to a perfect number. So there is a one-to-one connection between perfect number and the discovery of a Mersenne prime. And the complete details about Mersenne primes were given in this website, mersenne.org. The project was called GIMS, Great Internet Mersenne Prime Search, GIMPS. You can go to Google and type it. You get this website here that I have given you, mersenne.org, which gives you all kind of information about the discovery of Mersenne prime so far that we have done. And you can see that this is the latest Mersenne prime that is discovered. So I still remember during December 2018 when I was giving talk, I was mentioning in almost all the talks I was mentioning about this, because I was also a member in the GIMS team. Each member will be given a different name, like a pen name, and my pen name was Prime Hunter for this. So I keep getting all the updates and things that is done in GIMS. Okay. So there is a one-on-one connection between discovery of Mersenne prime as well as a perfect number. So once you know the 2 power p minus 1 is a prime number, you multiply that number with 2 power this minus 1, that is 2 power p minus 1. The product will give you a perfect number. So though we know the particular form for the perfect number, even today, even at the advent of so much of computing powers, we still only know 51 perfect numbers. And rightly, as Descartes said, the French mathematician philosopher said, perfect numbers like perfect men are very rare. So that's true actually, because among all possible numbers, perfect numbers, even as of today, we know only 51 among them. So existence of perfect numbers are very very rare. It is quite hard to find them. Now, the next idea that I will be discussing is about amicable numbers, which means that if you take 220 and 284, if you add all the proper divisors of 220 without itself, proper divisors means you should not include it as we saw before. So if you add all proper divisors of 220, you get the second number, 284. And if you do the same process for 284, that is add all proper divisors of 284 excluding 284, you get 220. So one gives the other. From 220 you get 284. If you do the process for 284, from the first I get second. If I add all proper divisors of the first number 220, I got the second number, which is 284. And if I add all the proper divisors of second number 284, I got back the first number 220. So first number giving second number and second number again giving the first number. Describing the friendliness of those numbers. Amicable, the term denoting for being friendly with one another. So these two numbers, 220 and 284, were treated to be friendly numbers or amicable numbers, whatever it is, because one explicitly describes the other. From 220 you get 284, and from 284 you get 220. So these two are amicable numbers, and this least amicable pair was discovered by Pythagoras or some of his followers. We are not sure about it, but they are known to Pythagoreans, the followers of Pythagoras. But many recent WhatsApp sources claim that Ramanujan was a great mathematician because he was the one who discovered the property. Was true. The WhatsApp message contains this property that if you add sum of divisors of 220, you get 284, and 284 gives 220. That is correct, but they attribute the discovery to Ramanujan, which is completely incorrect. See, I was telling in many talks recently that there are so many correct reasons and logical reasons. The exact reason for celebrating Ramanujan, who has done so much of work, good work in mathematics. So why should you attribute some other work to him and praise him? That is not that should not be done by mathematicians, especially those who teach mathematics should avoid all such misconceptions. In fact, there were other news like Ramanujan's formula was helping in activating debit card, credit card. It was because of only his formula that we are using debit card and credit card transaction, all those things, which were nonsense actually. That was not true at all. So we have to be very careful in choosing all those things. And then, so amicable numbers are giving this property with two cycle, in the sense that one gives the other and other gives it. So this from 220 you get 284, and then you get back 220. So this is two cycle numbers. And then you see there are no three cycle numbers. That is, if you can find three numbers A, B, C, for which sum of aliquot divisors, sum of all proper divisors of A giving B, and sum of all proper divisors of B giving number C, and sum of all proper divisors of C giving back A. So there are no triplets like ABC for which this property like two numbers will hold true. In fact, no one has found that, and they believe such triplet cannot exist. But there are numbers with four cycle, and there are 142 such four cycle numbers beginning with this number. This is the smallest number with four cycle. For five cycle, there's only one collection beginning with this number. So if you take 12496, this number, and find the sum of proper divisors of this, you get one other number, some other number. Do the same process for the second number, you get third number. Do the same process for the third number, you get the fourth number. Do the same process for the fourth number, you get the fifth number. And if you do the same process for fifth number, you get back the same number. This number 12496. This will repeat again. So this because it's a five cycle. And the largest cycle is found to be 28 cycles. It was discovered by Pauli. He said that if you take 14316, this number, and keep on doing the process, after 28 numbers, the 29th number will be repeated. So this is so far known to be the largest such number with this many cycles. So far, no one has discovered beyond this. There's only one number with 28 cycles. Okay. So these are the only things that we have discovered so far. And if you go beyond the two cycle, like four cycle or five cycle or six cycle or seven cycle, such numbers are called sociable numbers, because there's more length than what we expect. Now I'll rush through some of the things that we have to see. I love these figure eight numbers. Okay, I have chosen 2 or 3 topics for today. Figure 8 numbers are numbers where you have a beautiful connection of numbers with geometry. That is, you can view numbers through pictures. You can describe numbers through diagrams or pictures so that we can understand the basic inherent properties of numbers. And figure 8 numbers again were introduced by Greek mathematicians, especially by Pythagoreans, who were drawing this in science, this kind of pictures to analyze the basic properties that exist between numbers. Now, this is a visual proof for triangular numbers. See, sum of first n numbers, natural numbers is a triangular number. This is 1 plus 2, that is 3. 1 plus 2 plus 3. So, this 1 plus 2 plus 3 can be arranged in a triangular shape, and that is why it is called a triangular number. 1 plus 2 plus 3 plus 4 can be arranged in a triangular fashion, shape. So, this is a triangular shape. They add up to 10. 1 plus 2 plus 3 plus 4 plus 5 can be arranged in a triangular shape. This is a 5th triangular number. This is a 6th triangular number. And incidentally, if you look at this 6th triangular number is 21. Today's date is 6/2/2021. So the 6th triangular number, the date T6, that is 6th triangular number, is year number 21. So we are very fortunate to study these things here today. This is a very apt date for discussing these ideas. Okay. So the sum of first n natural numbers is the nth triangular number denoted by Tn. So to prove this, what I do is I stack a right triangle here, like taking with 1 plus 2 plus 3 up to n, and do the same thing. I take another copy of this and put it upside down along with this. So if I put another copy upside down to this, what will happen is this will add up to n, but this number will be one more. Because of the upside down stacking here, you get one more number here. So this is already n here. I'm adding one more here. So you get a rectangle whose dimensions are n by n plus 1. So that means you have n numbers here and n plus 1 numbers. Because up to this, there is only n. Because you put it upside down and stack one with the other, you get a nice rectangle over here. And this area of the rectangle is length times breadth. So that is, so area of this rectangle, I take 2 copies to get this rectangle. This is 1 plus 2 up to n. This is 1 plus 2 plus 3 plus 4 up to n. So I take 2 copies of 1 plus 2 plus n. So I'm taking 2 times triangular number Tn. So I get a rectangle whose area is n into n plus 1. Therefore, Tn is n into n plus 1 by 2. This kind of proof, what we call is proof without words. We have not done anything here, any calculation. Just picture conveys the answer. So that is very famously called PWW, which is proof without words. I love such proofs actually. I mean, any proof without much calculations or any number of equations is wonderful to see. And triangular numbers exist in several counting problems. I'll just give, because I took this problem because this were asked in many times especially in part 1 questions. So if you take 1, 2, 3, this particular set, and if you want to count the number of subsets of this set such that each subset will have consecutive digits, then the answer will be a triangular number. You guess the reason why this is so. So this are the 3 subsets of 1, 2, 3, this particular set, such that each subset have consecutive digits. Okay, so I can't write 1, 3 because 1 and 3 are not consecutive. I mean, they are one next to the other. Okay, so if you count the number of subsets in such that each subset have consecutive numbers, then there are 6 here, as you can see. So 3 and 6 are triangular numbers here. I can provide the reason. Reasoning is very easy actually. You can guess for yourself. For example, if you want to take number of subsets with consecutive digits beginning with 1, how much subsets you get? This is a subset beginning with 1. This is a subset beginning with 1. This is a subset beginning with 1. So there are 3 subsets beginning with 1 of the required property, and there are 2 subsets beginning with 2 of the required property, and there is only 1 subset beginning with 3. So you get 1 plus 2 plus 3. Naturally, 1 plus 2, sum of consecutive natural numbers is a triangular number, and 1 plus 2 plus 3 is 6. That is a triangular number, 3rd triangular number. Therefore, the answer is not surprising to us. And if you take any polygon and count its number of sides as well as its diagonals, so for a triangle there's no diagonal, so there are 3 sides and no diagonals. I want to add these 2, number of sides and diagonals. So this 3 plus 0, sides plus diagonals, is a triangular number. For any polygon, this will be true. So for quadrilateral, there are 4 sides and 2 diagonals. So this sum, 4 plus 2, 6, that is a triangular number. For pentagon, there are 5 diagonals and 5 sides. So 5 plus 5 is 10. As you can see here, 10 is a triangular number. 3, 6, 10, 15, they're all triangular numbers. This will always be the case. You can prove it generally. The general proof comes like this. For an n-sided polygon, there are n times n minus 3 divided by 2 diagonals. So if you add n to n into n minus 3 by 2, you get n into n minus 1 by 2. That is sum of first n minus 1 natural numbers. Therefore, the answer is a triangular number. So this is not very difficult to see. And if you now take subsets as we did here, but in a different sense, like 1, 2, what I am going to do is picking 2 element subset from the given set. This element has only 2 elements, so there is only 1 2 element subset from the given set. From this particular set, I want to pick subsets with containing just 2 elements, not more than that or less than that. So how many 2 element subset that exist from this set? 1 2 1 3 2 3. Just a subset. I'm collecting subsets containing exactly 2 elements. So there's only one subset with 2 elements. There are 3 subsets with 2 elements. There are 6 subsets with 3 elements. Here 6 subsets. So 1 3 6 10. These are all again triangular numbers. So these are all counting problems which are very frequently asked in the exams, like many competitive exams. So I thought the answers are surprisingly connected to triangular numbers. So if you take a circle and divide, draw a line, draw a chord or some line, so the regions are divided, you get some answers here. You see these answers are one more than the triangular numbers, so that I get maximum number of regions here. And this is called lazy Catter sequence, or some other sequence that you can call. Very famous sequence here. So this answers upon dividing circle through straight lines, cutting through straight line, just like a pancake. You cut the pancake through as many cuts. This is cutting by 2 cuts. This is cutting by 3 cuts also, so that you ensure that you get maximum number of regions. If you count the maximum number of regions by such cuts in a circle, the maximum number of regions turns out to be answers which are one more than the triangular numbers. And this is a very famous problem called handshake problem. Supposing there are 5 friends attending a party, assuming that each person shakes hands with every other person in the party only once, then how many handshake will take place? So for example, if there are only 5 persons attending the party, the first person may shake with all the remaining 4 persons that were marked with red lines here. So he may shake with all the rest of the 4 persons. He should not shake hand with himself, but only with others. So there are only 4 choices for the first person, and there are only, because the second person has already shaken with the first, he cannot shake with the first, which is already done before. So he can shake, the second person can do the process with only the remaining 3 persons. He can shake second person in the party, can shake with the third person, he can shake hand with 4th person or with 5th person. Already he has shaken hand with 4th person, so that is not possible now, because the condition says you can shake hand mutually only once. So I can't do that. So for the first person there are 4 choices. For the second person there are 3 choices. For the third person there are only 2 choices. Namely, the third person can either shake hand with 4th or 5th, not more than that. And the 4th person will have only 1 choice, and 5th person already have shaken with other people. Therefore, he doesn't have any choice. So if you count this, you get 4 plus 3 plus 2 plus 1, that is 10. So in general, this answer turns out to be a triangular number. So number of handshakes done in a party with this restricted condition turns out to be a triangular number. And these are the real life examples of triangular numbers. And you can see perfect number that we have done before. Again, I go back there, is also a triangular number, because it is, as I told you, it is always written as sum of first 3 numbers here, sum of first 7 numbers here. The second perfect number is 4 times 7, so that is 7 into 8 by 2, sum of first 7 numbers. This equation was already done before. Any number which is written as sum of first k natural numbers is a kth triangular number. So the first perfect number is the 3rd triangular number, second perfect number is the 7th triangular number, the third perfect number is the 31st triangular number. So any perfect number is a triangular number of this form. Okay, and you can make out nice equations like this. If you add 3 triangular numbers to the previous index of triangular number, you get another triangular number. That is 3 times triangular number with n plus 1 less than this. So if you have 5 dots here, you take only 4 dots here. If this is tn, this is tn minus 1. So 3 copies of the same triangular number and 1 copy of the previous triangular number will give you a big triangular number with 2n copies. Similarly, you take 3 copies of the same triangular number, but one added to the next number, one more than this. So this is 5, this is 6 here. So if you take the next triangular number, again you can stack them to get a bigger triangular number like this. So this kind of equations can be proved because you know that Tn is n into n plus 1 by 2. So using basic algebra, it's easy to prove this equation, not very hard. And in snooker and billiards, you always have balls arranged in this fashion. One ball first, 2 balls, 3 balls, 4 balls, and 5. They always stack only 15 balls with 5 rows like this. 1 plus 2 plus 3 plus 4 plus 5. You can notice in pin balls, that rolling ball, the spins will go up. Usually they keep 1 pin first and then 2 pins, then 3 pins, and the last row you have 4 pins. You have only 10 pins, and this numbers are triangular numbers. 10, 15 are triangular numbers. So this is used in pin ball games. This is used in snooker and billiards game. The triangular numbers exist there, and square numbers are the numbers which you can arrange in square fashion. And the number 12, which can be arranged in a triangular fashion, rectangular fashion, like 3 times 4, 3 rows, 4 columns, or 2 times 6, 2 rows and 6 columns. Either you can arrange this way or this way, both are same. So these numbers are called square numbers, and these numbers are called rectangular numbers. Okay. Generally, a rectangular number is how they form, m into n, where m is some number and n is some number. But you call rectangular numbers as oblong numbers or pronic numbers, P-R-O-N-I-C, pronic numbers, if it is product of 2 consecutive numbers. So 2 times 3 is 6. So this is also a rectangular number, because any rectangular number is product of 2 distinct numbers, like P times Q, product of 2 different numbers. In particular, if you take product of 2 consecutive numbers, then it is called it's called an oblong number or a pronic number. So these are special cases of this, and mathematicians through this pictures can say that all composite numbers are rectangular numbers, which means if you take any composite number, you can arrange them at least in 2 rows or 2 columns. Only the prime numbers are the only numbers which can arranged only in a linear fashion. Any prime number cannot be arranged in a rectangular fashion like this. As you can see, if you take 5, if I stack 5, 2 rows and 2 columns, you get only 4, 1 will remain. It will not form a rectangle. So any prime numbers are non-rectangular forms, numbers which does not form a rectangle. So it will be beautiful to see like this. Okay, and you see the number relationship here. Sum of consecutive numbers or some other numbers here, 4 plus 5. These are consecutive numbers, but adding these 3 numbers, you get this answer. Adding these 4 numbers, you get this. 9 to 15 are consecutive numbers. You see relationship here. So these numbers are square numbers. 1, 4, 9, 16. The left hand side numbers are square numbers. 1 square, 2 square, 3 square, 4 square. And these numbers are pronic numbers or oblong numbers. 2, 6, 12, 20, 30. You see the last numbers. So the first number here begin with square numbers, and the last numbers here are pronic numbers or oblong numbers. Okay, so this kind of relationship that you can always find. And this collection here is 1 less than this collection. So if there are 4 numbers here, you get 3 numbers here. If there are 5 numbers here, you get 4 numbers here. So once you know this collection, it's easy to write down the remaining collection, because this collection are consecutive from this, and this number of numbers here is 1 less than this. So if you have 5 numbers here, you get only 4 numbers here. So it's easy to guess actually. Similarly, if you take relationship between sum of squares of numbers, it's easy to see. You can see that these are all alternative. This is third triangular number, second triangular number. This is fourth triangular number. This is sixth triangular number. This is eighth triangular number. So square of alternate triangular numbers here, and this is 4, 12, 24, 40. As you can see, it's double of. It's twice this number, pronic number or oblong number. So 2 times 2 is 4. 2 times 6 is 12, 2 times 12 is 24, 2 times 20 is 40. So this, once you know this kind of patterns, it's easy to churn out numbers one after the other. This is quite easy to do. See, if you stack, I give this an exercise to school students usually wherever I go. This is T3, that is 1 plus 2 plus 3. This is T2, 1 plus 2. So if you add 2 consecutive triangular numbers, you get a square number. So you see the shapes are always squares. 1 plus 2 plus 3 plus 4. This is T4. This is T3. So T3 plus T4 is 4 square. T2 plus T3 is 3 square. and this is t4 plus t5, that is 5 square. In general, if you add tn minus 1 with tn, you get n square. So it's quite easy to do with basic algebra, but this way you see very nice answer. I mean, pictures conveys more meaning, isn't it? The picture is worth more than 1,000 words. So this kind of, and if you keep four see oblong number like 2 rows and 3 columns here, if you take oblong numbers and keep 4 copies of them and then add 1 to it, you get a perfect square. Like here we are having 6 here, so 6 is oblong number here. So if you take 4 copies of an oblong number and stack it around and put a 1 dot here, you get 5 square here. So 4 times an oblong number. So because you see the property, if you multiply this by 4 and add 1 to it, you get 9, which is 3 square. If you multiply this by 4 and add 1 to it, you get 25, that is 5 square. If you multiply this by 4 and add 1 to it, you get 48 plus 1, 49, that is 7 square. If you multiply this by 4 and add 1 to it, you get 81, that is a perfect square. So this kind of properties you can observe. And this is, you see, this is one particular square. This is 3 square, this is 4 square. So difference between 4 square and 3 square is added this here. There are only 7 numbers. So if you add 3 square with 7, you get 4 square. If you add 11 numbers with 4 square, you get 5 square. And 9 numbers, not 11, I'm sorry, pardon me. If you add 9 numbers, there are 5 here and there are 4 here. So if you add 9 numbers to 4 square, you get 5 square. So this diagram gives the difference between consecutive squares and how much you need to pile from getting one square to the next square. So visual representation. And this is of course 1 plus sum of consecutive odd numbers, 1 plus 3 plus 5 plus, if you get a square number. You're adding sum of consecutive odd numbers, you get n square. Sum of first n odd numbers is n square. Okay. Now this is another pattern. 1 plus 2 plus 3 plus 2 plus 1 is 3 square. 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1 is 4 square. So the square that you get is number of red dots in the middle. So this is 1 plus 2 plus 3 plus 4 plus 5 plus 4 plus 3 plus 2 plus 1, that is 5 square, and so on. This is 8 triangular numbers of equal size added to 1 is a perfect square. So 8tn plus 1 is n square. 2k plus 1 whole square. So this is a beautiful relation, and this relation is very important because you have a very nice theorem saying that if tn is a triangular number, then 8 times tn plus 1 is a perfect square. So if you multiply any triangular number by 8 and add 1 to it, you always get a perfect square. And that is because there are 8 copies here, 1 2 3 4 5 6 7 8. So we pile 8 copies of triangular numbers and add just one more in the middle, you always get a perfect square. Okay. And these are general figure 8 numbers. For the want of time, see, triangular numbers are with 3 sides, square numbers are with 4 sides. Similarly, you can construct figures of numbers with 5 sides called pentagonal numbers, with hexagonal numbers with 6 sides, and so on and so forth. The general formulas have a specific pattern here. The orth triangular, the figure 8 number is defined by this expression: r by 2 times n minus 2 into r minus n minus 4. So this is PR of n. Okay, the orth triangle. If you put r is 3 here, you get triangular numbers. If you put r is 4, you get square numbers. If you put r is 5, you get pentagonal numbers, and so on and so forth. There is a nice problem that you can make with this. If n is 4, how many squares are simultaneously triangular number? This is a very interesting number theory problem, but those problems, the solutions for those problems itself will take a huge amount of time for me to explain. So this is just list of them. So this list actually gives the number of, these are square numbers which are also triangular numbers. These are also pentagonal numbers which are triangular numbers. P3 means triangular. These are collection of pentagonal numbers which are also triangular. See, any hexagonal number is automatically a triangular number. Okay, so if you take all hexagonal numbers, by calculation, you see that any hexagonal number will qualify be a triangular number. And these are the other things. P4 is a square number. So these are all pentagonal numbers being a square number. This hexagonal number being a square number. And so this is a general formula for describing a square triangular number as well as square number, this collection. So if you put n is 1 here, you can see, you put n is 1, this 12 root 2 and minus 12 root 2 will cancel. You get 17 plus 17, 34. 34 subtracted by 2 is 32. 32 by 32 is 1. So that is the first number. If you put n as 2 here and simplify, you get 36. If you put n as 3 here and simplify, you get 1, 2, 2, 5, and so on and so forth. That is how you get. So what Fermat, the French mathematician, the genius mathematician who gave Fermat's last theorem and Fermat's little theorem, like a power p minus 1 is congruent to a, it's congruent to 1 mod p. He was a master in giving such beautiful theorems in number theory. So he mentioned in one of his work that I was the first to discover the very beautiful entirely general theorem that every number is either the triangle, which means what he was trying to say, that I will rush through because of the need of the time. What Fermat was trying to say is that every natural number is sum of at most 3 triangular numbers. Every natural number is sum of at most 4 square numbers. The square has 4 sides, isn't it? And same, any natural number is expressible as sum of at most 5 pentagonal numbers, at most 6 hexagonal numbers, at most 7 heptagonal numbers, at most 8 octagonal numbers. In general, at most n polygonal numbers. The general numbers are called figure 8 numbers or polygonal numbers because they form a beautiful polygon with that many sides. And mischievously, he was giving like this, as in the Fermat's last theorem, he was giving a marginal note here. I cannot give the proof here, for I intend to devote an entire book to this subject as true, because the proof is very lengthy. And to the effect in this part of arithmetic astonishing advances, see, Fermat was very clever, but he always concealed the proof with him. The most part he doesn't. He teases others with these claims and asks them and see how good they are, and he keeps on the trick with him. So that is how he worked. He was basically a lawyer, but has done so much of work in number theory. And now I come to concluding part of the talk with the discovery of a +2 student. He was staying near Delhi, some 60 kilometers far from Delhi, in probably a place called Gurugram or something. I don't exactly know the name. I hope it is Gurugram or something. This Utkarsh Kohli, I wrote to him. There was a mail ID that I got. I wrote back to him. He has sent this picture to me. We corresponded. What this boy has done, he is currently doing his 12th class. Okay. Now what he has done is this: you take any number like 56 or 1729 or what, he gave this property. So you take any number with as many digits, like 2 digits, or it can be 3 digits, or it can be 4 digits, or 5 digits, or 6 digits, or with any number of digits, natural number, of course. So you take such numbers, multiply each digit by 111 and add them. So suppose if I take 56 to begin with, multiply 5 with 111 and 6 with 111 and add them, you get this. The final answer is 1221. You do the same process for 1221. You take each digit and multiply by 111 for the new answer. You get some other number. You do the same process, multiply each digit by 111 and add. Ultimately, his claim was you always get this number, 2997. 2997. This is similar to the Capreka's constant 6174. But Capreka's constant will be 6174 is applicable only for 4-digit numbers. If you take 3-digit number, the Capreka's constant will be different, like it's 495. It's not 6174 always. But quite remarkably, this student's discovery will always give 2997, irrespective of what number you choose, with how many digits it can contain. The number of digits is immaterial, the size of the number is immaterial, and what number you take, it still works. That is quite remarkable. I mean, I was astonished to see this discovery at the first instance. Probably a few months ago, he gave this and published in a journal. So this only shows that India has immense talent and potential, and young students like Utkarsh Kohli, and thanks to people and students like him, today India's legacy in mathematics were preserved. In fact, I give another instance of such thing, like when we saw the amicable numbers here, the great mathematicians worked on. Pythagoras, I said, was the first one to discover the least amicable pair. And then other mathematicians like Fermat gave this pair. French mathematician whom I discussed now gave this amicable pair. Euler himself gave around 60 pairs, 60. So he gave around 5 dozen pairs of amicable numbers. And today we know more than 12 million amicable pairs. Thanks to supercomputers and high computing machines, we know more than 12 million amicable pairs. I'm not sure about what's the largest amicable pair as we know. I'm not sure about it. But people keep on discovering as when time progress. So there is no limit to such computations. Okay. But quite curiously, mathematicians like Euler, Fermat, Descartes gave some pairs, and several other mathematicians, even Gauss, those people had missed the second least amicable pair. The second least amicable pair, namely 11841210, was discovered by uh, a 10th class student of that time in 1866 in Italy. There was a student who was doing his 10th class. His name was Niccolo Paganini. Not now, but in 1866 in Italy, that student in 1866 was doing his 10th class, accidentally discovered this number. And when he mentioned this to other people, people were flabbergasted because they were so taken into so much of surprise, because how come this kind of small number with this not big magnitude, this was missed by great mathematicians of yesteryears. This was a very surprising thing, which only shows that there is still ample scope, and there is always place for discovering very new thing. Forget about others' discoveries. If you work patiently and work hard, and sometimes you may get failure, but if you keep on working with understanding the basic concepts well, and if you have patience and perseverance with you, you can always come up with new discoveries which can be missed by great people who lived before us. But nevertheless, mathematicians have been working tirelessly along to pursue this kind of relationship that existing. The wonderful thing about discussing number theory is that you don't have to have prerequisite in numbers. Like if you want to pursue research in graph theory, you know to have many definitions and basic concepts. Only then you can go to graph theory. Whereas if we want to pursue research in algebraic geometry or algebra, for example, you have to know the basic concepts in algebra. Only then you can go to even discuss what is what. But in numbers, like mathematicians like Fermat were not a trained mathematician, right? Mersenne was not a proper mathematician, but they did great work because numbers were followed by even amateurs. And it so happened that casually some people may come and give a property which were unnoticed by several mathematicians of previous years, and that will form a new theory also. There were such occasions. People of no identity have discovered some beautiful theorems in number theory. That is always possible only in numbers. And if you take this number 142857, I have given the proof of this. Of course, the student has not given the proof in the magazine that which he published. Then I provided the proof of this and published in this Monday's issue of Dinamalar Pattam paper to encourage such person. So I gave detailed proof of the outline of the proof of why this should work. And in fact, I found a more general pattern also for this. So I wish students and other teachers, young teachers, to see why this work. I'm not going to explain now because other things I have explained very briefly. So I leave this as an exercise. You can read the student's mind. And so there is, if a 10th class student can discover an amicable pair, and if a 12th class student can discover a wonderful relation like this, like multiplying something and getting always a constant for any number that you choose, why can't you do? Which means only to say that there is always a scope, as I said before, to discover new things. So there's nothing end to any process that you make, and that is the beauty in mathematics. So I like most about the ancient Greek mathematics because they always have chosen geometry and mixed that with numbers. So they played numbers with geometry. That is why it's called figure eight numbers. So this kind of identities and formula that we have done, most part have avoided equations. So you can understand why the equations are true through these pictures. So seeing formula through pictures or visualizing mathematics is one of the best things that a mathematician can have. Once you visualize concepts, it will give not only the truth, but it will give great happiness and joy in learning. And therefore, as far as possible, you try to visualize, because upon visualizing, you get great ideas in you, and you can possibly come up with beautiful things. And some of the quotes were already sent in welcome address and other in the beginning slide of this. So I want to avoid such thing now, but I want to convey this. According to Pythagoras, numbers rule the universe. That is true because even today we are using credit card, debit card numbers, houses identified by number, phone numbers, all things were concerned with numbers. Even if you write exam, you have to write your roll number, and if you want to purchase anything, you have to use your PIN number. For which, if you make any transaction, you want to have an OTP number. So whatever you want to do, you are bounded by numbers. So in one sense, what Pythagoras said was true. Even today, numbers rules the universe. That is quite true. And this part by Paul Adish, who was another of my favorite one of my favorite mathematicians, said, "Why are numbers beautiful? I know numbers are beautiful. If they aren't, then nothing is." So this is kind of things. And Kronecker said that the God made the integers and all else is a work of man. That is also true quite a way. But people who believe God can understand this. And of course, this quote was said by the speaker initially. Mathematics is the most beautiful and most powerful creation of the human spirit. And those who do good mathematics for quite a while can understand. This was said by Stephen Banach, a great mathematician, after whom Banach spaces were introduced. And then I want to quote at the end by Maria Mirzakhani, who recently passed away. She was the only woman Fields medalist, woman mathematician who made a big revolution in mathematics circles. She was very young when she died, around 42 or 41. She was not alive now, but she said she's an excellent mathematician who won Fields Medal in the year 2018 ICM. If you say mathematics is the most beautiful, how to identify the beauty in mathematics? Beauty of mathematics only shows itself to more patient followers. Only if you have enough patience and perseverance to follow the ideas in mathematics, you can observe the beauty behind the mathematics and do great progress. So with this, I conclude my presentation. If there are any doubts, I will be happy to answer. I thank everyone in the Department of Mathematics, DG Vaishnav College, the organizers, the convener, organizing secretary, and everyone for giving this opportunity and to share what little I know with students. Thank you.
Thank you, sir. Participants, if you have any questions, you can post it in the chat box. Sir, one question. Please send me the figure-eight number formula.
Figure-eight number formula I mentioned. It is r by 2 times n minus 2 into r square minus n minus 4. I mentioned in one of my slides. R by 2, the rth figure-eight number of order r is r by 2. In the brackets you write n minus 2 times r square, n minus 2 times r minus n minus 4. That gives the, if you put r is 3 there, you get triangular numbers. If you put r is 4, you get square numbers, and so on and so forth.
Thank you, sir. Thank you, sir. Mathematics is the queen of all sciences. Number theory is the queen of mathematics. Thank you, sir, for the wonderful presentation on the explanation in number theory. I hope all the participants are really very much benefited. The feedback link will be posted in the chat box. Participants can fill the form and submit. So the next program is C4. So we have C4 class today at 6 p.m. And the next webinar is on an introduction to linear programming problems, graphical and simplex method, presented by Pragya Mishra, Lucknow, on 13th February 2021, and the time is from 10:30 to 12 noon. I now invite Dr. Vaidya Subramanian, Assistant Professor, PG and Research Department of Mathematics, to propose the vote of thanks.
Thank you, ma'am. Thanking is a gesture. By his blessing and grace, we are able to make today's national webinar what it was. On behalf of the entire fraternity of our mathematics department, my sincere thanks to our management, our secretary, Sri Ashok Kumar Mundra ji, and our beloved principal, Dr. S. Santosh Babu. A real heartfelt vote of thanks to our speaker, Dr. R. Sivaraman, Associate Professor, PG and Research Department of Mathematics, DG Vaishnav College. Today, we had the opportunity to hear about, to know about, to learn about, to explore about number theory. So, sir has given the different classification like perfect numbers, amicable numbers, like that. Sir has classified the entire number theory. Thank you, sir. Thank you for your enlightening lecture. Organizing an event over a day is not possible. Even in a day or a night, it's not possible to organize an event. At this juncture, special thanks to the organizer, Dr. N. Jayant Karthik, Associate Professor, PG and Research Department of Mathematics, DG Vaishnava. Thank you, sir. In near future, more events we are expecting from you, sir. Thank you. Special thanks to the captain of our ship, R. Venkatraman, Professor Head, Department of Mathematics, DG Vaishnava, who has shown the platform for this. I thank him personally for giving me this opportunity. Thank you, sir. I also behind the scene to execute this event both technically and non-technically. Thank you all. Last but not the least, without you, the participants, the program may not get succeeded. It may not. I thank each and every participants. Thank you all. Thank you.